great enthusiasm. We have two speakers today, and our first speaker is Natalia Adukova from Aberystwyth, and she will be talking about the exact matrix polynomial factorization.
Good afternoon. My name is Natalia, and I'm a PhD student at Aberystwyth University. Firstly, I would like to thank the organizers for the invitation to this workshop. I present the joint work with Professor Adukov and Professor Mishuris. Today, I will speak about the exact Wiener-Hopf factorization of matrix functions. Also, we will discuss the difference between the explicit and exact solutions of the problem. So the main message of my talk is to show you that now the exact factorization of matrix polynomials is fully automated process and very easy for the user. So if as you can see from the title of my talk, it is the abbreviation for the name of our package, the ExactMPF. Okay, in the last part of my talk, I hope that I will be able to show you some examples on the laptop. But we start with some preliminary information, a few definitions and important facts about the factorization. Okay, firstly, we have to consider the Wiener algebra W. Here we have the definition for the matrix Wiener algebra, since I don't have enough space on the slide, but the definitions is similar. So we start with the Wiener algebra. It consists from all continuous functions that expand into an absolutely convergent Fourier series on the unit circle. So the matrix Wiener algebra, it consists from matrix functions of order P with elements from the Wiener algebra that expand into an absolutely convergent Fourier series on the unit circle. Okay. Also, we need to define two subalgebras, W plus and W minus. As you can see, all functions from W plus expand into an absolutely convergent Fourier series in non-negative powers, while in W minus in non-positive powers. So after all this preliminary information, we are ready to define the factorizations. So the right Wiener-Hopf factorization, it is of matrix A. It is its representation in the form 1, where D is a diagonal matrix function, and these integers are called the right partial indices, and GW are the groups of invertible elements. If all partial indices are equal to 0, we call such factorization canonical. So we have the definition for it here. Also, we have to consider the left factorization as well, because we can't permute matrices. We know that the operation of matrix multiplication is not commutative. But the definition is similar to the right one. Okay. Also, it is important to highlight some important facts. Any matrix function from the group of invertible elements admits the VH factorization. The partial indices are uniquely determined by the matrix function A. In contrast, the factors are not determined uniquely. Okay. Yeah. After these 5 days during the workshop, I think we know that the VH factorization method is widely applied in a lot of different areas of mathematics, mechanics, engineering, and physics. And here we have some of them, but the list is large. Unfortunately, apart from all good news, there is a bad news too. There are some obstacles for the use of this method. The first obstacle, the absence of explicit formulas for constructing the factorization. The second one is that the factorization problem is, generally speaking, is not always stable. Okay, now let's discuss each obstacle in more detail. In the general case, there is no a solution for the factorization problem, but only for a few special classes of matrix functions it is possible. So in our research, we will concentrate on the class of matrix polynomials. The matrix polynomials for which the explicit formulas have been developed. Unfortunately, even if an explicit method exists, some steps of the algorithm can be done only approximately. And if we have the unstable case, even the explicit algorithm won't be a solution. So let's move to the second obstacle. So the factorization problem is called stable when the partial indices are stable under a small perturbation. Here you can see the definition for it. So there is a question how can we understand when partial indices are stable or not? There is a well-known criterion, GKB criterion, for the stability of the partial indices. Unfortunately, again, the GKB criterion is not effective in the general case because there are no explicit formulas for the partial indices. So even if the explicit methods has been known, evaluation of the partial indices may require computation that can be in turn unstable. So we can say that generally speaking, the factorization problem is not always stable. Okay, so what can we do in order to overcome these obstacles? So as I already said, in our research, we concentrate on a special class of matrix functions, matrix polynomials. So for this class, as I mentioned, the explicit formulas have been developed. So the first problem is solved, but we still have to sort out the instability issue. So, in order to eliminate this, we will solve the problem exactly because in this case, the stability question does not arise. By the explicit, by the exact solution, we understand the fulfillment of these two points. However, even the exact solution doesn't exist always. So we have proven the criterion for it to happen. Our theorem states that A admits the exact VH factorization if and only if its determinant is exactly factorable over the Gaussian field. It is worth to note that there is no such criterion for any other classes of matrix functions. So, as I already said, Generally speaking, the factorization problem is not always stable. So it is a very important requirement to solve the problem exactly. Here, I want to highlight that our package finds the exact solution for it. And what do we have in the exact solution? We have the explicit formulas for the partial indices and for the factors that were developed by Professor Adukova. And in this case, in the explicit, we realized them in the exact arithmetics. In other words, we conduct all calculations in the field of the Gaussian, in the Gaussian field of rational numbers. So in this case will be always stable. And this is very important point for us to solve the problem exactly. Yeah, as a result of our project, we have developed the exact algorithm for the factorization of matrix polynomials and realized it in Maple software as the package ExactMPF. Today I won't tell you any details about coding and the steps because it's quite difficult and will take a lot of time. But in the end of my talk, I will provide some links to our articles where everything is explained in real detail. So, but I would like to pay your attention that this is the only one existing package that allowing the automated factorization. Moreover, the right and left factorizations are found simultaneously. We believe that our package may have a lot of applications, and main are listed here. Also, it is important to note that we already have some successful cases of the application of our package. Okay, yeah. This slide shows the user's point of view on how our package works. You input a matrix polynomial and then the package starts to check. Is it possible to find the exact factorization for it or not? If the answer is yes, you will get the full answer, the right and left factorizations and the partial indices. If the answer is no, you will get the notification that the exact factorization is not possible. I hope to show you soon how it works on the computer, on some examples. As I already said, our package is fully automated, and the potential user doesn't have to worry about any checkings of the input data, and as well the same applies to the output data because the package does everything by itself. But here, let's discuss a little bit which check-ins the package does and why are they important. So, firstly, we have to check, is a Lorentz polynomial? Why do we need to do it? Because we can work only with them. So, the second check, it ensures that we will avoid approximate calculations. The third one is quite obvious, yeah, because we consider the VH factorization problem. And the last one, the determinant should be exactly factorable, because here we calculate, because the calculation of the coefficients requires computations. So if the determinant is exactly factorable, then these coefficients can be calculated exactly. So if everything is okay, yes, yes, and yes, if all 4 points are true, it means that we can use the method of essential polynomials in the exact arithmetics. If something wrong, one of them is wrong, so unfortunately the exact factorization is not possible in this case. I prepared examples, checking examples for each point, and we will see what happens in the package. So here let's have a look on 2 simple examples on the slides, because it's very easy to see the results in this form rather than in the package. Then I will solve them in the package as well, and we can see what we will get. So in the first example, we get the exact factorization is possible, and we get the left and right factorizations. So here I highlighted the matrix D in red in order to pay your attention that the partial indices can be different, and this is okay, this is normal situation. Also, if we remember the conditions for the GKB criterion, we can make the conclusion about the stability. Let's go back a little bit, and yeah, this one. This is the stability, the criterion for the stability. So the difference should be less or equal to 1. So let's go to our example, and yeah, I think maybe it will be we will write them on the board, because in the examples we will use them. Here the difference is equal to 0. So this is the stable factorization. This one here we can see that this is unstable factorization. But the very important point that we managed to find it, and the answer is correct. So let's move to the next example. Here we have modified our first example in one of the entries. It is highlighted in red. So in this case, the exact factorization is not possible, and I hope that we will see why soon when I will show you it on the computer. Now we are going to consider some examples. Firstly, we will do checking examples of our 4 main points. Then we will see some triangular matrices, factorization of triangular matrices. Then in triangle we will have, I think, have one that with complex coefficient, and then we will try to do some experiments with multiplication and exponentiation, and I hope that in the end we will have some time to your example. Maybe someone will be happy to provide a very simple matrix, and we will try to solve it. Unfortunately, my regular laptop has some problems, so today I'm using quite old laptop, and so we have to limit ourselves by very simple examples. So let's start with checking examples. Checking examples. So the first one is the first one is we need to check is a run polynomial. So let's run the program. Yeah, we have my matrix A, and yeah, during the preparation of the program, I found out that we need to add a special notification for this case. At the moment, the program has produced an error, but we will fix it in the next release of the program. We will add the correct note why the exact factorization is not possible here. So let's try this one. Here I added a square root, and of course the package recognized it and give us a note that the exact factorization is impossible. So let's try this one, and again the exact factorization is not possible because I think you can see that because of these two elements, matrix A won't be invertible on T. So the next example, I think it is our second example from the slides. And here again we don't have the factorization, and let's finish with some good one. So this one is our first example from the slides, and you can see how fast the package done it. And here I think maybe I will show you again the example. Please look at this. Can you see the factors here? And the factors that we got here. They can be different because they are not determined uniquely. It's okay. It's normal situation. Okay, let's move to the next portion of examples, and it will be very quick. I think I will show you very quickly. 2 by 2 triangular matrices. The lower triangular matrix, we got it. And let's try the upper triangular matrix again. We got it. And the 3 by 3, a little bit longer, but again we got it. So now let's try to do some to see some experiments. So I will show you a part in the program and second part in the PDF file, because this computer is quite old and it will take a lot of time to compute. So we start, and what will we do here? We will take matrix A, matrix A1, A2, then multiply them in this order and then in this order, and try to look at the partial indices. What will happen? Of course, all this it doesn't have any theoretical justifications, but it can be very useful for some experiments, maybe for some checking some hypotheses. Okay, let's try this one. So here we have we multiply, and as you can see, our partial indices, and let's try it in the different order. Yeah. So sorry, is it? Yeah. One more. Okay, you can see, yeah, that in this case they are changed. I mean, when you change the order of the multiplication in this way, in this particular example, the partial indices are changed. We have it for this order and for the previous one. Yeah, and let's try quickly this one. And here, they won't change. Again, we can't say anything about it, but it can be useful. So also we can use our package for experiments with multiplication. A little bit more difficult, and I will scroll a lot of here, and we will see the final result. So we have this matrix, and we will try to put it in a power. So what can you say? Yeah, here we will have, like, we can, like, to find some tendencies how our partial indices can behave. Yeah, again, it can be very useful. Maybe we can see that they are stabilized when the power is increasing. The partial indices may stabilize, and etc. So quite useful. And I want to. I'm sorry. I want to finish my talk with the final example. Again, only in the PDF, because it will take a lot of time. I won't tell any theoretical background. You will hear it in a few minutes. Let's just highlight the idea. We create the matrix A. And it is important to note that no one can find the partial indices for such matrix, but we introduce a very tricky way. So what we will do, the general idea, we will approximate our matrix A by AN, for which we can apply our package. We can apply our package for the AN and find its exact factorization. So let's have a look. Yeah, we formate the approximant. Then we find the right factorization of it. Yeah, the right factorization of it. It takes a lot of time, quite long example. It took, I don't remember how much time, but quite a lot of. So then, sorry for this. Then we normalize the plus and minus factors, and here we find the radius of the canonical factorization. This radius, it will, in this neighborhood, all matrix of will admit the canonical factorization, and then we need to find norms R minus and R plus, and yeah, the same for factors plus. And in the end, we estimate the difference between A and AN. And so A was our original matrix function, AN is our approximation. So there is a question. Is the original matrix in this neighborhood? And the answer is yes, it is clear. Here we have delta. This is an estimate for our difference, and we can see if delta is less than 11. Yeah, here 11. Yeah. If we look at the radius, it's here, yeah. So if it's less, then in this case, oh, I'm sorry. Ah, yeah. One moment. Yeah.
No, no, it's
thank you. So in this case, yeah, we found the factorization. Okay, sorry, I think I'm late. Sorry. Yeah, yeah.
All right. Right. Okay. Ian.
So you avoid instability by using exact arithmetic. Would there be, I mean, obviously Maple's perfectly capable of doing exact arithmetic with radicals in it. So would there be any, would you gain any generality by allowing it to have radicals as well as rationals?
I think we don't think about it yet at the moment.
I mean, my guess would be that it would produce a huge mess, but it might gain some generality, I don't know.
Okay.
I didn't understand that last example. In that last example, did you approximated the sign by a polynomial,
yeah.
And then in the end you were able to recover the sign. Like your final answer seemed to not be. It was back.
Yeah. We find the.
How did you get back to the sign from the polynomial approximation?
I see this question to me for the next talk, so let's.
Okay, hard question.
Maybe someone else will ask.
Yeah, because the theory wasn't provided yet. It was like a preliminary example for the next talk.
I'll ask after Gennadi's talk.
Okay. Right. Last question.
I have a very simple question. Have you considered the possibility to port this from Maple to some open source?
Yes, a good question. We know that the Maple it requires a license, so not everyone can pay money for it. So for the license, we are thinking to rewrite it in Python. I think it will be like a next task for us.
Right. Shall we think? I'll speak again.